I'm the Institute's teaching officer and academic director in physical sciences. My own background is in materials science. I have a particular interest in the atomic level structure of materials and how those affect their properties. What I'm going to do this morning is I'm going to take some rather ordinary materials and we're going to explore what it is that I think makes them really special. So we're going to start back in the 17th century. Now, the first true microscopes had been built in about 1590, and they were followed quite shortly by telescopes. So the scientists of the day were rapidly beginning to appreciate that they'd really got some very powerful optical instruments in their hands that would allow them to look at materials, at the world around them, out into space in ways that they'd never been able to before. So what we have here is a selection of works from Robert Hooke. Now, apparently there are no contemporary portraits of Robert Hooke, so I can't show you what he looked like because we don't know. But what I have done is I have found one of his microscopes. And what Robert Hooke was able to do was to make very detailed records of what he saw through that microscope. As well as being an excellent scientist, he was also a very skilled illustrator. And he assembled many of his observations, his scientific recordings, into a book, which is this one, Micrographia, or some physiological descriptions of minute bodies made by magnifying glasses, with observations and inquiries thereupon. This plate on the right comes from the book, and it's one I particularly like. It's a collection of illustrations of frost. And he talks about what he sees in the frost. I've very often in a morning, when there has been a great hoarfrost, with an indifferently magnifying microscope, observed the small styriae or crystalline beard, which then usually covers the face of most bodies that lie open to the cold air, and found them to be generally hexangular prismatical bodies. Now, his dedication to his work and the chilliness of 17th century houses becomes apparent when we realize that he's actually observing the ice crystals in his chamber pot. The title of the figure on the right is actually Several Observables in the Six-Branched Figures Formed on the Surface of Urine by Freezing. However, he will have understood that what he had in his hands was a very precious instrument, and it was something that allowed him a privileged view of the world around him at a level that nobody had been able to see before. So I'm very pleased to take inspiration from scientists like Robert Hooke, because it's an extraordinary privilege to be able to look at the world at that kind of level. It's an extraordinary fact that all of the complexity in the world around us comes from a number of building blocks, a number of atoms, which is hardly greater than the number of people in this room. That's a very useful piece of understanding, but knowing that something is true like that is a different matter from understanding why it's true and understanding why that complexity builds up. So that's one of the things that led me to be a materials scientist, wanting to understand why it is that things around us are as they are. Let's stop for a minute and think about what materials science is actually trying to do. What we want to do is we want to understand how materials is structured, and we do that starting from the atomic level, working upwards. We want to understand how that structure influences the properties of the material. We want to understand how to exploit those properties. Then we want to understand how to modify materials so we can get new properties, different properties, properties that we want. And we'd also like to be able to develop entirely new materials. What I'm going to do is I'm going to actually concentrate mostly on the first two. That's why we're going to look at some rather ordinary, everyday materials that are quite well understood to get some understanding of how that process works. Now, my own particular interest is actually in looking at materials at a scale which is something like 10,000 times smaller than what Robert Hooke was able to see. The ability to do that came with the invention of electron microscopes in the middle of the 20th century, and this one here on the left is one of the modern microscopes housed in the Department of Materials in Cambridge. It's actually one which is mostly used for tomography. It collects a series of images which can be reconstructed to form three-dimensional views of complex materials. My own particular interest is not so much in tomography, but in a collection of materials called hybrid frameworks. And those are rather like the zeolites that we're going to look at in a minute. So, what we're going to do then is we're going to look at how materials are structured, we're going to look at how this influences their properties, and we're going to do that by looking at some ordinary materials. And I hope that by the time we get to the end of this lecture, you'll be able to leave the room with some of the same kind of sense that Robert Hooke had of just how wonderful the world is if you look at it really closely. We're going to set off by looking at brass, small piece of brass. Now, brass is an alloy. It's a metallic combination of copper, one nugget of copper, and zinc. As you add more and more zinc to copper, the material gradually becomes harder and more difficult to work with. And in practice, if you try to go above about 50% zinc, find you can't really do anything terribly useful with it. So all commercial brasses have lower zinc contents than that. But we still do plenty with it. Brass is a very versatile metal. It's been known for something like 5 millennia, but unlike bronze, which is an alloy of copper and tin, for most of that time, we actually haven't been able to do very much with it. Because until the 18th century, there was no way to extract metallic zinc, so we couldn't make brass in any great quantity. So all of the kind of uses that we see for brass today have largely developed over the last 200 to 300 years. And we now use it for a huge range of purposes. So, for example, we have functional items. We have taps, pipe fittings. This is a filter down at bottom right. But it's also widely used for decorative purposes. This is actually a beaten brass headdress, photographed from a Dutch museum. The Romans used it for high-value items. They prized it for its decorative properties. That's a Roman Sestertius, and widely used for musical instruments. Brass is actually surprisingly strong. It's almost comparable with mild steel. Its strength and its toughness are not very different from an ordinary steel, but we can't use it at quite such high temperatures. Brass would melt not very far above 900 centigrade. A steel will last for about another 600 degrees to somewhere over 1500 centigrade. Of course, we can't use it over all of that temperature range. Brass does have one big advantage over steels, which is that it behaves much better when it's exposed to the elements. It just acquires this greenish-brown tarnish, and it's not unattractive. It doesn't erode in the way something like a mild steel would. Something which is also coming to be of interest is the copper content of brass actually turns out to have antimicrobial properties, and we're beginning to go back to thinking that brass might be a very good choice for fittings like in places like hospitals, which are hygiene critical. So, what do we see when we look at the microscopic structure of brass? Well, that varies quite a lot depending on exactly how we've treated it. It also depends on how much zinc is in it. But it doesn't vary in a random way. It varies in a way that we can control and exploit. So here we're looking at the right on a polished surface of a sample of brass which had about 30% zinc in it, and it's been annealed. It's been held at several hundred degrees for long enough for the structure to settle into a very organized kind of arrangement. The image comes from an optical microscope, like this one, very much like this one. It might even have been this one at the top left. So it's come from an imaging system which has a light source, it has lenses, it has a camera. That's a modern-day successor to the kind of microscope that Robert Hooke was using. Before we go any further, we should stop and think about the scale of this image. This whole image has come from an area which is about 1.5 millimeters across. Now, each of these little individually coloured regions we describe as a single grain. So those grains are about a 20th of a millimetre across, and that means that this image here is about the size of a single grain of sand off the seashore, and within the volume of a single grain of sand, we'd find probably about 30,000 of these little tiny individual grains. Now, those are actually quite big grains for a metal, which is why it makes such a beautiful image. Typically, they'd be significantly smaller than that, and something like the size of a grain of sand might contain more like 1 million grains of metal. Okay, so that's one possible way that we can see brass. But that's not the only way, and it depends very much how we've treated it. So let's look at it and see how it comes, if it comes straight from a casting. This is the same composition, same kind of amount of zinc. What we see then is very different. We see elongated, angular, branching structures in clusters. You can see that there are sets of them all parallel to each other. These rather leaf-like structures we call dendrites. And each aligned one is an almost perfect crystal, like our original grains, but it's got a much more complicated form. Let's keep looking. Here's another brass. It's got a slightly higher zinc content. We can still see our branching dendrites in here, but now we've got something else. These dark regions in between aren't holes, they're a slightly different material. What has happened is that dendrites have all run into each other, but as they do that, our brass, our molten brass, has begun to separate out. It's separated out into two phases, one with a little bit more zinc, one with a little bit less zinc, and rather like oil and water, they don't mix too well. So as the dendrites form, we end up with one of our two phases trapped in the branches in between. Let's up the zinc content again. So these are the first two images we looked at. These two have even more zinc in. They've got about 40% zinc, and that's beginning to be at the limit of what we see commercially. We can see the same kind of thing. We've got a mixture of two different kinds of structures, and in lots of places it's beginning to break up completely. We're now seeing things that look more like platelets. These two, and particularly the one at bottom left, have what we call a Widmanstätten structure. And if any of you have been up to astronomy, and you've been to any talks there, or you've seen some of the samples that they sometimes have out on show, you might have seen this, not in a brass, but in iron meteorites, which are exceptional because they produce beautiful Widmanstätten structures because of the way they've cooled as they enter our atmosphere. Okay, so why does this happen? Well, it's actually easiest to think about if we've got a good idea about what happens in 3 dimensions. So here on the left, we have a single nugget, not of brass now, but of copper. This is a natural dendritic formation because they occur very commonly in both in materials but also in geological samples. This is a natural copper nugget. It's come from a mine in Kazakhstan, and the formations are ones which occur very commonly when materials solidify from a melt. So you can see here how it's grown with a trunk and the little side branches, and it's spreading out in a very tree-like, fern-like kind of way in 3 dimensions. This is a metal alloy, but it's been treated in a rather special way, so we can see the dendritic structures here. These are the cobalt dendrites because the other phases have been etched away, so we're left just with the dendritic phase, just with the cobalt dendrites standing proud, almost like Christmas trees, inside the structure. And this is very much like what we would see and what is happening inside the brasses we were looking at just now. Now, if you take a structure like that and you section it through flat and you look at it in an optical microscope, you then see the sections through the main trunks of our dendrites and through the side branches. And you see something which looks a bit like this. Now again, this isn't a brass, although it is another copper alloy. This is a copper phosphorus alloy. And you can see here we've got the main stem of a dendrite and its arms. And you often get these parallel rows of blobs where we've cut through a dendrite stem but not cut through its core. So they look as if they're floating free, but actually they were attached either above or below the surface we're looking at. That copper phosphorus alloy produces very beautiful dendritic structures, but I have to confess that it's actually completely useless, and I know of no use for it apart from showing people what dendrites look like. Now, in order to understand what's happening and why it's happening, we need to go a little bit further into this structure. So let's start here at top left. This is now the crystal structure of copper. We've got a small cube. We have an atom at each corner of the cube, one that we can't quite see at the back, and another one in the middle of each face. And if we as we start adding zinc, the zinc atoms can be accommodated in that structure just randomly. They just go in wherever they happen to be. The structure doesn't really notice it's got some stuff that isn't copper in it. And it can go up to about 35%. Now, obviously, we do that actually from the melt, but I've done this little animation to show you what happens because it's quite surprising how much 35% of a second species of atom is. So you can see we stack up these individual little cube units in 3 dimensions, and we end up with a complete crystal structure. And each of those grains that we looked at in the first micrograph is a large stack with many thousands and millions of these little units in it. So if we try to add a bit more zinc, we can't go on doing this forever, because after a while, we get to the point where zinc and copper are actually slightly different sizes. They have different numbers of electrons, and the atoms simply don't fit in that structure comfortably anymore. And they start to arrange themselves differently. They need to be arranged more like top right. So now we've got cube again, copper atom at each corner, but they're closer together than they used to be. And we've put a zinc atom in the middle. Now that's what happens when the structure is completely ordered, and it'll work really nicely, provided that we have exactly 50-50 copper and zinc. We don't have 50-50 copper and zinc, so if we have less zinc, or if we make the structure at a slightly higher temperature, above about 400 centigrade, we don't form the ordered structure that we're looking at bottom right. What we actually form is a slightly more random arrangement of the two, but still with this, what we call body-centered cell, instead of this face-centered cell. Let's think about the sizes of those a little bit. Each of the grains that we saw in our original micrograph was about 100,000 of these units across. What that means is that inside a single metallic grain, there would be about 1,000 billion units. Inside a piece of brass the size of a grain of sand, that scales up to something like 30 trillion of these little units. So we're talking quite big numbers, all stacked up in order. Okay, now let's go back to our dendrites. Let's think a little bit about how they came to be there in the first place, because they can't just appear from nowhere in solid brass or in anything else. In fact, they're a characteristic of solidifying many metal alloys and also geological materials from a melt. And what this movie is going to show you is dendrites, which are the blue solid objects. This is a theoretical model, it's not real material. Blue dendrites, they're going to form from a cold solid front on the left, and they're going to extend into the hot red liquid on the right. run it once. And you can see in this case, this is modelled for a low-carbon steel. It's forming just one phase, so all the blue stuff is going to run together. In the case of our brass, what's happening is that because it's rejecting the high zinc content material, higher zinc content material in between the dendrite arms, we end up with these beautiful dendritic leafy frond structures and the second phase trapped in between them. So, what have we got? We've now got two different, slightly different structures. One can accommodate slightly less zinc, one can accommodate slightly more zinc, and any real structure is some kind of combination of the two of them. Now, our basic face-centered unit gives us a material which is strong. We can work it, we can shape it, we can hammer it, even if it's cold, and it's fairly tough. The body-centered structure, which has a little bit more zinc, more like 40–45% zinc, gives us a material which is stronger. It's harder, but it's more brittle, and that means that we can't work it effectively, even when it is hot. What we have in a real brass is the structure organizes itself into a combination of these two, and that gives us a kind of composite material. So what we end up with is a material where, by controlling its composition and by controlling the way in which we manufacture it, we can control its properties as we need them to be an optimum by combining these two. So that gives us an example of how the principles of understanding things in material science lead to an understanding of the structure. What can we do with it? Well, brass has some characteristics we mentioned at the beginning. Manufacturing is pretty low cost. We can machine it, it's strong, it's tough, and all of these three we can adjust by controlling composition and the way we treat it. It's pretty corrosion resistant. It's also highly recyclable. Almost all of the brass that we use in this country is actually recycled. It's not made from scratch. And that gives us the huge range of places in which we can use it, all the way from decorative items and musical instruments to hardware and spark-resistant components in mines. Metalworking, of course, is and always has been a highly skilled trade. And the metal workers of previous centuries worked out that we could do the majority of these things and worked out how to do them effectively without understanding what the reasoning was for why that was the case. We now have a much better understanding of the relationship between structure at a low level and properties at a high level, and developing modern high-performance alloys relies on that same process. It relies on an understanding of how the properties we get macroscopically are related to the fine-scale structure. So, although it requires high-level, good experimental work, good experimental optimization to get modern alloys, it's now all informed by a good, solid, and often theoretical modeling and understanding of how that relates to the properties that we actually get. Okay, so let's go on and look at something rather different. Now, this is rather less aesthetically interesting, shall we say, than brass. What I want to look at next is zeolites. Now, zeolites are amazingly commonplace materials. On macroscopic scale, they're really rather dull. They turn up in things like pet litter. We use huge tonnages as water softeners in laundry detergents. They turn up in things like aquarium filters. They're really not, on this scale, looking terribly interesting. So why have I got them in there? I've got them in there because of this. Because when you go straight in to the atomic scale, you see that these very unexciting macroscopic zeolites are extraordinarily beautiful crystal structures. Zeolites have been known like brasses since antiquity. The Romans built parts of their aqueducts out of zeolitic tuff, and there is some thought that this may actually have contributed to them being able to maintain clean water supplies. They weren't really used in any great quantity until the 1950s, when the first commercial zeolite was synthesized and came into manufacture, and about the same time commercial mining of natural zeolites started. This is that very first zeolite that was commercialized in the 1950s. It's called Linde type A, and what we're looking at is a structure which is made up of oxygen, which I have colored purple, and it links lots of green atoms, and the green atoms are representing either aluminium or silicon, and exactly which is which depends on exactly how we made it in the first place. Now, one of the features of zeolites is that everywhere you go in here, every time we have one of our green atoms, it's surrounded by 4 oxygens. It makes a little tetrahedron. So if we take I suppose slightly over a quarter of this, and look at it a little larger, we can fill in those tetrahedra. And we can see that one of the defining features of a zeolite is that it's completely formed of linked aluminium or silicon and oxygen tetrahedra. Now, what we're looking at here is actually just one projection of the structure. We're looking at it flat. It's got big holes in. Now, that's quite unusual. Metals don't have any holes in at all. They had a kind of connectivity which we colloquially tend to describe as electron glue. They're held together in all 3 dimensions. This is a structure which is held together more as a framework. So it's got big holes. Holes are quite interesting. The holes are actually much bigger than the gaps that we just saw. They look rather like a football, actually. So a big pore in the middle and access into it through the edges. On the right, what I've done is I've just put an imaginary yellow sphere inside that pore. So you can see that the size of the hole is a lot bigger than the size of the channel that lets you into it. Okay, so we then take this one little unit and we build it up into a big structure. So here's our zeolite framework, now filled up with pores coloured yellow to show you what they look like. Although our yellow spheres are imaginary, the pores aren't actually empty. The aluminium, the silicon, and the oxygen together, if they just sat there as a framework, would be carrying a lot of negative charge, and they can't do that. We've got to balance the negative charge up somehow. So typically, a zeolite will fill up those pores with other stuff to balance the charge. It might be hydrogen ions. In the case of Linde type A, it's often sodium ions. But we have good access to those pores. We've got big holes, and other things can flow through the zeolite system. So that gives us the kind of properties that we find we need to work with our zeolites. For example, let's take laundry detergent. That's used about very nearly 1.5 million tonnes per annum worldwide. That's not the detergent, that's just the zeolite water softener that goes into the detergent. What happens there is we load up our zeolite with something like sodium. In the course of your washing, that sodium swaps with calcium and magnesium that make the hard water in your washing machine. The water can flow through the pores because all of the molecules are quite small enough to get in, and as it passes through, the calcium, the magnesium, the things that make the hard water swap out with the sodium or with the hydrogen ions that are in there, and you end up with softer water. We can load up zeolites with metals for catalysis. They're very widely used as petrochemical catalysts. They're also beginning to be getting quite a lot of interest generate quite a lot of interest with nuclear reprocessing. One of the things that happened after the Fukushima accident was that there was a large amount of controlled dumping of zeolite into the sea around Fukushima, because the contaminated heavy metals can flow into the pores in zeolites. They're trapped by the structure of the pore. The remaining harmless metals flow out, and you then have your radioactive material trapped in a way which you can safely handle. We like handling solids. We know exactly where they are. They're easy to work with. Quite often, there's a lot of energy given out or taken in when things change places in the pores. So we use zeolites in places as thermal collectors or even as refrigerants. They're also used as molecular sieves. They are indeed atomic sieves. Only things of the right size can get through the holes. So they find applications, particularly in medical science, as molecular sieves. Where we're slightly less concerned about composition and structure, the natural zeolites get in on the act, and they turn up in things like animal feed, pet litter, all sorts of adsorbent properties. And worldwide, we run through very nearly 3 million tons a year of natural zeolites. And actually, about 2/3 of that is both mined and, I believe, used in China. Most of the deposits, the large deposits, are in the Far East. Now, an important feature of the two sorts of materials we've looked at already is the way that they're connected together. The metals were connected essentially three-dimensionally with our electron glue. The zeolites were connected into a framework structure with our sequences of oxygen tetrahedron. What we're going to do now is we're going to look at another group of materials which have a different kind of connectivity, and we'll see how that affects their properties. So we're going to look at plastics, completely ubiquitous in everyday life. They got into everything in the last 50 or 60 years. Materials scientists have a little bit of a problem with terminology here. We don't like the word plastics very much because we're already using it. We use plastic to describe the property of materials when a material changes its shape in a way which is irrecoverable. So something like the dent that I made in the side of my car a few weeks ago is what we describe as plastic deformation. It's never quite the same afterwards. So plastics by material scientists will always be described as polymers because that allows us to focus on what the material is and what its structure is without getting mixed up with properties which could also belong to other things. And they come in an extraordinary range. So, for example, we have clear plastics, we have translucent plastics in the translucent bottle, we have completely opaque plastics, like the one on the circuit board. We have hard polymers, like the one made into the plug. We have ones which are quite soft and stretchy, like plastic bags. We can have ones which are hard and tough, like the plug again, or ones which are hard and rather brittle, like, for example, plastic cutlery. Some of them are quite resistant to high temperatures, so we have medical polymers which can be sterilized. Others will degrade, melt, deform at that kind of temperature. Some of them will even burn at high temperatures before they break down into anything remoldable. We're going to look at a particular subset of polymers, which are the ones that I think are particularly interesting purely because of their visual appeal. I just think they make wonderful images. They're just brilliant to look at. The ones I want to look at are the colorless transparent polymers, because they do something rather special when you look at them between two sets of Polaroids. So we've got a little piece of a protractor here at the end of a ruler. And one of the things which is common to many of these polymers is that they can be what we call injection molded. So you can form them by forcing molten polymer into a mold, the size of whatever object you want, through a small orifice. And we can see in these images between the Polaroids coloured fringes, which of course aren't there before we had Polaroids in place, that trace the flow lines of the polymer through the mould. So it's very clear on the ruler. You can see there's been an entry point at the bottom. The polymer has flowed up into the length of the ruler, outwards towards the sides, and somewhat backwards into the corners, although it's obviously having a bit more difficulty getting in the corners. And the coloured fringe is roughly traced the way that it's gone. The protractor is the same. There's an entry point here, just by the 90-degree line, and you can see that it's flowed inwards from there and then outwards down in the two directions. Same kind of effect in the two on the right. This one at bottom right is some biodegradable plastic cutlery, and you can see there are very complex flow lines, particularly around the spoon bowls. This is the bottom of a polyethylene terephthalate cup, and again, we've got a complicated flow pattern, complicated pattern of contours where the polymer is flowed out around the base of the cup. Now, I'm going to focus on one particular polymer because it produces this effect very nicely. This is one called polyhydroxybutyrate, and like all polymers, it's a long linear molecule, and it's made up of little units. And these little units are our monomers. Here's one of our monomers. So let's take a quick look at that. Well, we've got 3 carbon atoms in a line and an oxygen, and those are the ones that are going to form the backbone of our chain. So notice we're now connected only in one dimension, where everything else we've looked at has been connected in all 3. 3 carbon atoms and an oxygen. We've got an extra carbon and 3 hydrogens hanging off on one side, an extra oxygen, and a couple of hydrogens hanging off the chain. So that gives us our little unit. And then, of course, we've got lots of those. Now, I just drawn everything out in a straight line when I made this diagram, and that's not quite right. And one of the reasons you can see it's not quite right is that the hydrogens and the oxygens are a bit too close together. I forced this all to be straight. It's also rather short. A typical polymer unit, a typical polymer molecule rather, could be 1,000 or even thousands of these units long. On the scale of this kind of molecule on the image here, that puts the other end of the molecule somewhere out in the garden. They're extraordinarily long compared to their width. Now, I've drawn that out as if it's completely straight. And here's another one. This is a small segment of a model of a polythene molecule. And I've deliberately gone to the effort of making it straight in order to take the photograph. But actually, most polymer molecules curl up. They rotate around these carbon atom centers, and they'll coil up quite a bit. What happens when we try to pack these molecules together? Well, if they're all straight like this, they pack together rather like bunches of dried spaghetti, just like dried spaghetti straight out of a packet. Because if they try to pack together any other way, there's vast amounts of empty space, and that's really very inefficient and not the way materials normally behave. If they're all curled up like this, they pack together more like cooked spaghetti in a bowl. And actually, cooked spaghetti is a pretty good model for what a lot of polymers look like. Some bits are neatly lined up, some bits are all coiled and twisted together. What we now know is that very many polymers actually do something which is a bit of a combination of the two of these. They tend to form little clusters, I suppose you describe them, which we call spherulites. And within these clusters, if they're the kind of molecule that straightens out fairly easily and packs together fairly neatly, we get little lamellae, where a molecule has come along and it's folded backwards and forwards on itself, sort of concertina fashion, for a while. And this all happens out from the center, and another one will go off in a different direction, and another one, almost like one of those sort of fluffy woolly balls, or woolly pom-pom that you get on top of a hat. In between, of course, things don't work out quite so nicely, and we get lots of ends of disordered chain, and lots of bits of what we call amorphous polymer, which are these randomly coiled chains stuck in between. Now, the reason I wanted to look at polyhydroxybutyrate is that polyhydroxybutyrate does this better than almost anything else that I know of. When you look at it between crossed polaroids, we can see these spherulites, which are almost big enough to see with the naked eye. These are about 0.5 millimeter across, so we can't quite see them with the naked eye. We do need a microscope. It's made them so effectively that there's no amorphous gaps really in between. You can see they've run into each other. It's almost like a bubble foam. So we've got straight boundaries where one spherulite has grown outwards, run into one coming from a different direction. And again, we can see coloured fringes in here. You can see them better in the magnification, which tell us something about the way that the polymer molecules are oriented, the way that they're flowing. The two pictures on the right actually come from not an optical microscope, but from a scanning probe microscope. And they're looking at the surface topography of spherulites. So they're actually looking at the surface contours. And it looks rather like a fossil. It reminds me very much of an ammonite. You can see a kind of snail shell sort of circular pattern on here. Not quite so clear in the bottom right picture, but it is still roughly there. You can see it very clearly, the same kind of spiral in the optical micrograph. What those are telling us about is that the lamellae in the spherulite aren't just going outwards, but that as they go, they're twisting along their length. And what we're seeing in these images is the pitch of the twist. Every time it goes round once, we get a fringe. So we have, within one material, from one kind of molecule, two different kinds of structure. And in that sense, polymers have a lot in common with metals. We can make crystalline regions, and we can make amorphous regions. With metals, we have two different kinds of crystallinity. Here we have crystalline ordered arrangements and disordered arrangements. So what does crystallinity give us with polymers? It tends to give us higher density because things are better packed, more heat resistant, less permeable to gases. Generally we get materials which are stronger, they'll be harder, but they also tend to be more brittle, they'll break more easily. Amorphous polymers aren't quite so well packed, they're a bit lower density. They soften more easily. They're rather more permeable to gases, more elastic. That's where our soft plastic bags tend to be made from. Generally softer, but they're also tougher. You actually have to put more effort in to break them. Because we can make these two kinds of structure, both from a single kind of material, we can play the same kind of game as we saw with the metals. By optimizing the way that they're combined, we can end up being able to tune structures in ways which allow us to optimize properties to get a variety of properties in a controlled way out of a single material, or in the case of polymers, of course, we have many base molecules that we can start with. Now, I've spent the last 40-45 minutes looking at three rather everyday examples of how we can use the principles of materials science to understand what we get from materials. Just to finish up with, I'd like to draw your attention to a set of videos which have recently gone up on the university website. These are all titled Under the Microscope, and it's a collection of about 14 or 15 short videos, just a minute or two, which show mostly current research, but particularly striking examples of looking at materials on a fine scale. I've picked out three which here come from the physical sciences. There are lots of biological examples as well. There's one about stretchable electronics. This is a very, very thin gold film on a kind of rubbery substrate. And you can see in the video how it stretches and recovers. the aim of this is to be able to think about how can we make electronic devices which we can bend. You know, can you wrap your iPod around your wrist? The middle one is about growing nanowires. So again, we're thinking about very, very fine scale potential for electronics. And each of these little wires is only a few hundred atoms across, and you can watch them growing in real time on the video. The right-hand one doesn't come up so well in a still photograph. It's great on the video. But this is a liquid crystal pixel structure and some examples of something that we hope will create much higher resolution displays than what's now possible. So if you want to have a look at those live, if you go to the University of Cambridge website and to the research pages and search for Under the Microscope, you'll find the whole series and you can look at the whole lot of them. So what I hope I've been able to do there is to explain to you some of the reasons why I think materials science is such a fascinating area, why I share Robert Hooke's interest and excitement in what he found with microscopes in the fine structure of materials. But that's a very personal choice for me. So the last thing that I wanted to end up with was just to remind you that there are a variety of science courses in all kinds of areas that are presented here at Madingley.